Today we are going to discuss the module 3 of the course Integrated Circuits and Applications. So coming to the module 3, in this module we will discuss the basic construction of differential amplifier and its configurations. So after completion of this lecture, students can be able to understand the construction of differential amplifier by using one of the configuration of uh, transistor, namely the common emitter configuration, and also the different types of differential amplifier we will discuss here. So in order to construct a differential amplifier, usually we will take two common emitter configurations, and the emitter terminals of the two transistors are combined via the emitter resistor. So here, out of the three types of configurations of transistor, we know that common emitter common emitter configuration will provide higher voltage gain, current gain, and power gain over the remaining two types of configurations. And that's why, because it is highly compatible for amplifier, common emitter is used. Type of configuration is used for construction of differential amplifier. In the same manner, the input impedance is 1K, and the output impedance is also moderate. For this common emitter configuration, it is preferred over common base and common collector because it's suitable for amplification rather than the rest two types of configurations. So this is, we all know that this is the basic construction of common emitter amplifier, and here you can see that the emitter terminal is like grounded via the emitter resistor, and here you can observe the bypass capacitor, and VCC is the collector, like a DC voltage connected towards the collector terminal of transistor via the load resistor or the collector resistor RC. And if you measure the V out, the output voltage of CA amplifier, V out can be analyzed as VCC minus IC RC, where IC is the current flowing through the resistor RC. And here beta represents the current gain of CA amplifier. Usually beta value is very high. And coming to the construction of differential amplifier, here in order to construct a differential amplifier, we have taken two similar CE amplifiers. It's that similarity in such a way that the RC1 is equal to RC2, that is two collector resistors of the two CE amplifiers are equal, and in the similar manner we are going to take RE, that is we are going to match the two emitter terminals, or we are going to connect the two emitter terminals of those two transistors via a common emitter resistor RE, where RE is a parallel combination of emitter resistor of first transistor and emitter resistor of second transistor. So here in this equation you can see that RE is a parallel combination of RE1 and RE2. And what are the inputs? The inputs are applied to the base terminals of Q1 and Q2. So inputs are V1 and V2, and V1 is connected to Q1 base via source resistor RS1. Similarly, the input V2 is applied to the base of transistor Q2 via source resistor RS2. And here the inputs are V1 and V2, and the output is V0, which is the difference between the two collector ends of the transistors Q1 and Q2. So here V0 is proportional to, or we can say that V0 is equal to Vc1 minus Vc2, because Vc1 is given the higher potential over Vc2. So that's why V0 is equal to Vc1 minus Vc2. Or else we can say that V0 is proportional to the difference of the two inputs. So this type of coupling of two emitter terminals via resistor RE, which is a parallel combination of RE1 and RE2, is called as emitter coupled differential amplifier. So the ultimate thing is that In order to construct a differential amplifier, we will take two CE amplifier configurations, and the two emitter ends are coupled, and the two transistors, the characteristics of two transistors are similar. That is RC1 is equal to RC2, and two DC supplies are also equal, that is VCC, and the negative power supplies are equal in magnitude, that is minus VEE. So here you can see the definition. It is a type of electronic amplifier that amplifies the difference between two input voltages but suppresses any common input voltage. So this amplifier amplifies the difference between the two input voltage, because here you can observe V0 is proportional to V1 minus V2, and it is equal to Vc1 minus Vc2. That's why it is named as emitter coupled differential amplifier. So if you take the symbol of a differential amplifier, ideal differential amplifier, it has two inputs. One is non-inverting input, and other is inverting input. And here V0 is the difference between, it's proportional to the difference between V1, which is at higher potential, minus V2, which is at lower potential. So the same thing we have represented as a circuit diagram, which has shown in the earlier slide. So here input 1 and input 2 are applied to the two transistors Q1 and Q2, and the emitter terminals of Q1 and Q2 are coupled via resistor RE towards minus VEE. And V0 is V1 like Vc1 minus Vc2, or proportional to V1 minus V2, where V1 and V2 are the inputs and Vc1 minus Vc2 is the differential output. And usually there are two modes of operation of differential amplifier. One is differential mode and other one is common mode. In the differential mode, the two input signals applied at base terminals of the two transistors are equal in magnitude but opposite in polarity. That is, the two input signals are 180 degrees out of phase. And the second one is common mode, where the two input signals are equal in magnitude, and in terms of phase also they are equal. So the differential gain is defined as V0 is equal to the output voltage under differential mode. V0 is equal to differential gain A suffix D into V1 minus V2. So V0 is equal to AD into VD, or differential gain can be written as the output voltage divided by differential input, which is V suffix D, which is nothing but V1 minus V2. And another gain is common mode gain. So this gain is when the system is, or when the differential amplifier is operated under common mode. Here the common input V suffix C, common mode input V suffix C is V1 plus V2 by 2, or V0 is equal to the common mode voltage gain multiplied by common mode input. So total output voltage due to differential mode and common mode is equal to AD into VD plus AC into VC, where AD is differential gain, VD is differential input, that is V1 minus V2, and the AC is common mode voltage gain, and VC is common mode input, which is the average of the two input voltages. And this common mode rejection ratio is defined as the ratio of differential voltage gain to that of common mode voltage gain. So in order to reduce the common mode voltage gain, this factor CMRR must be a higher value. Ideally, CMRR is equal to infinite, and practically CMRR is equivalent to some 90 decibels. This is the ability of a differential amplifier to reject a common mode signal, because we are going to identify the difference between the two inputs. So we have to reject the common mode signal. So this is one of the factor which analyzes the state of the differential amplifier or the particular IC. These are the various applications of differential amplifier in volume control as well as the like amplitude modulation. Similarly, in automatic gain control circuit, we will use this differential amplifier configuration where the emitter, the two emitters will be joined towards, or you can say that the two emitter terminals are coupled via the common emitter resistor. The difference of two input signals can be amplified by using our differential amplifier. These are the various applications of differential amplifier. And in almost all the ICs for op-amp construction, that is IC 741 construction, this differential amplifier is used. So like several applications of differential amplifier are there because differential amplifier is a basic element for construction of op-amp. So op-amp is suitable for varieties of applications like addition, subtraction, multiplication, similarly integration, differentiation, like so many applications are there. So for all those applications, again, this differential amplifier in turn is used because op-amp has so many applications. So various configurations of differential amplifier. So we know that there are two inputs terminals and two output terminals are available. The two input terminals are towards the base terminals of Q1 and Q2, and the two output terminals are the collector terminals of Q1 and Q2. So based on that, there are four configurations. One is dual input balanced output, where we will apply two inputs and the output is taken at both the ends. Second one is dual input unbalanced output. Third is single input balanced output. And fourth is single input unbalanced output. Here you can see the dual input balanced output configuration where two inputs are applied here and output is the difference between the two inputs. So this model is suitable for all kinds of applications. So two inputs and output is taken as a balanced mode, under balanced mode. That is the difference of two connector ends. And second configuration is dual input unbalanced output. So two inputs are applied, but output is taken at any one of the collector end. That may be collector of Q1 or collector of Q2. This runs at highest frequencies. And the bandwidth range is up to gigahertz. And here slew rate is very high. That is in the range of 10,000 volts per microsecond. And this is suitable for broadband and IF communication applications because of its gain. And here the gain is less compared to the dual input balanced output configuration. Third one is single input balanced output configuration. In this configuration, only one input is applied either at base of Q1 or base of Q2. For example, if you are applying input at base of Q1, base of Q2 must be grounded. And it is because it is balanced output, output is taken at the difference between the two collector ends of the two transistors. And here you can say that it's also having high slew rate and it's used in communications and instrumentation systems. And here, because it is balanced output, the gain is also good and it has excellent DC performance. And the frequency, the bandwidth is like it's from hundreds to megahertz, like hundreds of megahertz range. And this is single input unbalanced output. So one end is of the input is applied and other end of input is grounded, and output is taken at only one of the collector end. That can be at collector of Q1 or collector of Q2. So it operates in the megahertz range and it is used for low power precision applications. And this is like an economy model. So out of the four models, dual input balanced output differential amplifier configuration is suitable for all kinds of applications. And this differential amplifier will have high input impedance and have low power and low noise. And even the gain is also very less for this differential amplifier. So this, coming to the I think from this module, students have learned the construction of differential amplifier and its 4 types of configuration. Thank you for listening.